everybody. If you don't know me, I'm Dan Kaminsky, and it is great to be back at Blackhat. So, I've got some good news, and I got some bad news. Good news, we're going to fix this thing. We kind of have to. We have no choice. The global economy is sort of based on a bunch of toys that are really good at moving pictures of cats. Unfortunately, we have no choice. We have to fix this. An economy where you have to be big enough to field a cyber army in order to participate is a really broken economy, not least of which because it's not like the particularly big guys are doing a great job. They're just affording the failure. The bad news is that we're not going to fix these problems according to dogma. If I can get my timer to start, by the way. The status quo is not working. Our mechanisms of defense are failing. And the thing is that dogma is really useful because, my God, there's a whole bunch of ideas even worse than what we're doing now. So it's an interesting challenge figuring out how to do things new and survive. So let me give you guys a riddle. What is the fundamental difference between attack and defense? When an attack doesn't work, you can tell. Offense has an inherent quality filter, put up or shut up. That doesn't mean that there aren't bugs in offensive disclosure. I mean, we have some questionable stuff out there, but it's not the same. The reality of defense is we have too much dogma. We've kind of gone from a perspective of, well, you can't defend against everything, to we don't even have to show what we're defending against. And then the critiques of the dogma don't ever say, hey, you're not defending against enough. The actual metrics are never there. So, if nothing else, this is a talk about skepticism. This is a talk about the processes by which we identify effective defenses to real and legitimate threats we can't ignore. Guys, you should not come out of this talk agreeing with everything I have to say. Just because I said it doesn't make it a good idea. Also, just because I said it doesn't make it a bad idea. My goal is to show you some new ideas and to start some discussion. This is the only way we're going to get defense to work. Now, lest you think there's nothing concrete here, there is a fundamental test that we do not do. You take 2,000 machines with a suggested defense. You take 2,000 machines without. Come back in 6 months. See if there's a statistically significant difference in the infection rate. Maybe we don't go through this process, but let's at least identify a gold standard when we see it staring in the face. The time will come when we spend as much money on security research as we spend on medicine. But look, medicine took hundreds of years to absorb science, and they had dead bodies all over the place to motivate them. We don't have dead bodies. We also don't have hundreds of years. The modern security era has been going on for maybe 10 or 15. But we've got to fix these problems. And there are vendors out there who care about stuff along these lines, and all I can say is reward them. So we have three heads to the security hydra. We have an inability to authenticate, we have an inability to write secure code, and we have an inability to bust the bad guys. What we're not going to talk about today is authentication. You want to talk about DNSSEC? Go pull me aside later. I don't have time to talk about it. We're not going to talk about busting the bad guys, because really there's no consensus on bad guys. My personal worry is about the people who are, breaking into every single one of the Fortune 500, let's be honest. Aurora, not the recent one, but the one a few years ago, was really nasty. And I'm really worried about the effect on small business. Like, entire payrolls being stolen and banks saying, well, sucks to be you. Sucks to be you is not an effective strategy for maintaining small business in the United States. But others have different priorities. What we're here to talk about is the inability to write secure code. Now, I'd like to clarify. I'm not saying it's impossible to write secure code. It's not impossible to deploy a PKI based on X509. It's not impossible to bust the bad guys. It's just plainly and utterly improbable, at least in most organizations. My perspective here is that possible is not enough. We have to get to probable or we failed. So what are we actually going to play with today instead of just talking about meta issues? I've got 5 subjects for today's smorgasbord. We're going to talk about timing attacks. We're going to talk about the generation of random numbers. We're going to talk about SQL injection. We're going to talk about the manipulation of networks that is getting increasingly popular. And we're going to go back to what I started at Blackhat talking about. We're going to talk about scanning the internet. These are all things that are possible today. How do we make them more deployable, less expensive, more probable? So let's start with timing attacks here. Many systems are modeled in terms of just what data they send, not when they send it. It turns out when data is sent often actually leaks security-sensitive information. According to a paper by Crosby, Wrighty, and Wallach, it's actually possible to find timing differentials over the internet on the scale of 15 to 100 microseconds, and on the LAN, down to 100 nanoseconds. Nate Lawson and Taylor Nelson did this amazing talk at Blackhat a few years ago, looking at string comparison functions, and they were actually breaking OpenID and OAuth with microsecond differentials. It was beautiful. So the proposed fix for these issues was basically to say, no matter what you're doing, it should take the same amount of time. So if I have 2 strings and I need to compare them, they're going to take the same number of microseconds, the same number of nanoseconds. Or at least the amount of time it takes will not be correlated with how far along in the string you got. Now, the problem is this. You have to do this every time there's a security critical comparison. You can't do it all the time because it actually dramatically impacts performance. So now you need to go through all of your code and identify all the critical comparisons. This is possible, it's just not probable. So, as a solution, I seem to note that distinguishing against internet noise yields less accuracy, 15,000 to 100,000 nanoseconds, than LAN noise. There we get all the way down to 100 nanoseconds. That's 3 to 4 orders of magnitude just because there's some noise and delay, and the noise and delay isn't even random. What if it was? There is a single line command in Linux that says, take this network interface and make it as slow as the internet, TC and the rest of that. For all packets emitted from this interface, add between 1 million and 3 million nanoseconds of delay. Call it a Boltzmann filter. At minimum, this means LAN should end up as secure as the internet. Maybe internet attackers are also impacted. This is a lot easier to deploy. It turns out that really matters. Has anyone here ever scrubbed their code looking for timing attacks? Yeah, like 2 hands go up. I can guarantee you more than 2 or 3 hands of you have timing attacks to worry about. Now here's the question. Does this actually work? So I figured out the way of basically saying it actually has to work. OpenSSH, when it does password comparison, does it using string comp. String comp is actually not constant time. It depends on how many characters you match. Now, the difference is literally in single-digit nanoseconds. In fact, very small number of cycles. Either this defense works, or I just dropped O'Day on OpenSSH, aren't I awesome? Yeah, I don't think I actually just dropped O'Day on OpenSSH. There's a limit to how much you can recover over networks. This isn't CSI, we're not enhancing. How much timing noise of what nature will permanently obscure how much timing signal beyond the point of infeasible return? We actually don't know. Somewhere between 1 nanosecond of noise and 1 day of noise, you're not getting the signal back. There's likely to be an equation here. We don't know what it is. Now, there is only so much noise you can ask for before the performance guys come back and say, stop. You're not allowed to put like 100 milliseconds of noise on every packet we send. But is it 1 millisecond? Is it 3? Is it 5? You might be able to ask for that. What could actually go wrong here? Well, the distributional lag from the interface may actually be bad. I mean, this was not designed for very, very low latency noise injection. The noise injection may be quantized. Could be Gaussian when it needs to be uniform. It could be uniform when it needs to be Gaussian. There's also the fact that every packet that comes out in TCP tends to have a timestamp associated with it. It's at a 10 millisecond level, but that may actually be on a tight edge. So we could fix all of this, but it has to matter that the canonical solution, constant time comparison, is a pain in the butt. The perfect solution is constant time comparison. The good solution is just to slow everything down out of the interface. You have to care that the perfect isn't being deployed before you consider making the good any good. Let's talk about something else here. Let's talk about RSA, that time where RSA got broken. Is it just me, or do we just keep hearing in the press that RSA is broken? Like totally alien bugs, right? Like one time it's about smart cards, one time it's about secure ID. No, this time I want to talk about where about 1 out of 200 RSA keys on the internet were badly generated. That's an incredible failure rate. I mean, I don't know about you, but if I ever broke 1 out of 200 things on the internet, I'd be happy. At the time, the break was blamed on RSA itself. There are 2 primes in RSA. If either one of them is repeated, you can basically get the other and get all of it. So the conclusion was that RSA was bad from Hughes and Lenstra. No. You've got a bad random number generator. It doesn't matter if it's RSA. Like, all ciphers are broken. And that was actually the point of last year's Fidelius trick. I basically used a password to create a random number stream, and then I used that random number stream to go ahead and generate RSA, DSA, and ECC keys. Because the actual stream was dependent on this password, if you knew the password, you could recover the private keys. What Lenstra and Hughes and Henninger actually have shown is that we actually have a lot of trouble with random number generators in the field. When the Debian bug happened, we got a little lazy, and we thought that was just Debian's bug. Turns out a lot of people are having this issue. Weren't operating systems supposed to fix entropy gathering once and for all? Well, they gave us devices, dev random and dev urandom. Dev random stops if it has no more bits. Dev urandom does whatever it can, and it'll always give you something. But what's happened is that we basically have only 4 accepted sources for random numbers. The hardware random number generator, the keyboard, the mouse, and maybe disk rotation because error is involved. Now here's the problem. Most of the environments that are actually out there that need random number generators don't actually have any of these. Our actual environments, desktops, okay, they got a human, they got a keyboard and mouse. They also sometimes less and less have disks. Servers sometimes have disks. VMs, nothing. Embedded devices, absolutely nothing. The reality of hardware random number generators is they're just not there. Yes, I know Ivy Bridge from Intel, their top-of-the-line stuff is going to have hardware random number generators, and we're all celebrating in 2012. Guys, we've shipped like billions of devices that have nothing. And yes, I know TPMs are supposed to have hardware random number generators. For some reason, every piece of code in the world treats these things like they're radioactive gunk that's going to blow up the operating system. I don't know why. Also, embedded hardware very, very rarely has hardware random number generation. So what's happening is best explained by analogy. You go online and you say, oh my God, protein causes cancer. Here's a link. Carbohydrates cause cancer. Here's a link. Fats cause cancer. Here's a link. Alcohol causes cancer. So you don't consume proteins, carbs, fats, or booze. You know what you do? You starve. This happens all the time in science. If you go ahead and get a little too obsessive, another failure mode will come to bite you on the butt. So here's what actually happens. And how do I know this? I actually talked to developers. Try it sometime. They have some code that depends on the random device. Their machine boots up. It needs to go ahead and generate a key. The random device has none of the things that will seed entropy. The operating system freezes. The application freezes. The embedded device fails test, goes back to the dev. What does the dev do? Dev rips out dev random and puts in something crappy. This is what happens every single time. Now, what perfectionists have thought would happen is that they'll go back and say, no, we need new hardware. And that's not actually what happens. What happens is they say security has failed us once again. Let's go ahead and ship something that works. So it is actually perfectionist theory that has caused 1 out of 200 RSA keys on the internet to be easily broken. We can do better. So there's a hack called TrueRand, and it's very old, it's from '96. We have to start looking at where we actually are getting random numbers from. Why do we like measuring keyboards and mice? Well, because you got humans and you got computers. And not only are they not synchronized, but we do not operate on a nanosecond clock. It's just not how we work. So what you're basically doing is you're measuring a slow clock with a fast clock, and that's where you're getting your noise. Any system with two clocks has a hardware random number generator. The biggest lie in your computer is that there's only one computer in there. There's dozens, and they often have their own clocks. Even if the error between the clocks is 1 part per million, guys, we got megahertz going on. That's a bit a second. The error is generally much larger than a part per million, too. It's why your clocks keep drifting. So TrueRand would go ahead, and what it said is, we'll go ahead and run the CPU in a tight loop, and every 16 milliseconds we'll fire an interrupt. This is where the entropy comes from. The interrupt is a slow clock every 16 milliseconds. The CPU is a fast clock, sometimes on the scale of gigahertz. Then they do a bunch of stuff to shuffle in case this is crap. This is not a bad solution. It actually works, but it's totally been disowned. And that's tragic, because 1 out of 200 keys would have been secure if it hadn't been. The perfectionist argument is, since we cannot model the behavior, we don't know how good or bad it is, we shouldn't do it at all. Over the years, Linux's random number generation has gotten worse and worse because we've been looking in fewer and fewer places to find bits, because we're paranoid and obsessed and wrong. We're just wrong. So I've been playing with something called DockerRand. DockerRand is an update to the old model. It has multiple generations, multiple sources. So I'll go ahead and I'll see how long sleep lasts with the various clocks that are available. Clock monotonic, clock real time. There's actually a CPU clock. You can see how many cycles the CPU has advanced with RDTSC. There's an incrementer. We see how many times we can increment an integer within a certain time period. This causes 100% CPU load. There's a real-time clock. There's actually a IR. Who's thought of IRQs lately? There's actually IRQ wired up on every PC that gets pings every controllable period of time. So you can say every 128 hertz or every 8,000 hertz. But my favorite, of course, is threads. Why threads? Because anyone who thinks computers are deterministic devices has clearly never written threaded code. So thus I have my favorite named hack of all time, 2 threads, 1 int. 1 thread adds, 1 thread subtracts, and every 10 milliseconds or so you see where the 2 threads have collided. And there's variations of that as well. And so what do we do with all of this data that we get out? Well, first thing we do is we throw it all into an actual cryptographically strong hash, because there might be more data than expected. So we just keep updating hashes with whatever values we get from the generators. However, we don't count them as useful bits, not immediately. There's a thing called von Neumann debiasing. You basically take 2 sources, you decide if they're zeros or ones. If they're a 0, 0, you throw it out. If they're a 1, 1, you throw it out. If it's a 0, 1, you count it as a 0. If it's a 1, 0, you count it as a 1. So what we do is we basically say, if we have that differential, then we'll go ahead and we'll count that we've received a bit. And I get the differential by summing the number of 1s in the output. So at whatever scale we get entropy, whatever bit it's living in, it should show up there. And then we actually insert into the hash a 1 as well, or a 0 as well. Third thing we do is scrypt. Scrypt is basically a time memory hard function. It goes ahead and says, well, you've got this blob of 256 bits. We're going to make you spend a bunch of memory and a bunch of time to turn this into an actual key. Why? Because if someone wants to guess the key, we're going to make them pay for it. And then we use the output of scrypt as a seed into AES 256 in counter mode. And we basically get a stream of an arbitrary size. This is what I think is the approach should be used. So let's mess with me. Attacking DockerRand. Find a platform where this fails. Guys, you have a ton of platforms. You have a ton of generators. They can't all work. Try to break it. Some suggestions. The kernel only visits user space so often. and may actually visit it at predictable offsets. So it may be that when I go ahead and get timing, my timing checks are too quantized, and I'm losing a bunch of entropy, even if I have nanosecond clocks going on. A bigger threat is auto-clocking. I might end up measuring a clock against itself, which, of course, clocks tend to be everything is highly correlated with its own identity. For example, the real-time clock, which I might normally think is a separate device, might actually be emulated by a hypervisor. And it might be emulated by the same clock that the underlying clock monotonic function is. So VMs, more than anything else, might ultimately fail. That being said, I actually run this on VMs, and the damn thing works. There are issues with cloning of virtual machines. The security model that I think I can say is an independent read to this function, to this dev random emulator, whatnot. Each independent read should be independent. So you can go ahead and split two VMs right before the instruction where the thing is called, and you should get two wildly different streams of randomness. After that function is called, there's nothing I can do for you. Is the underlying use of cryptography safe? Well, this is a modification of von Neumann. I'm not going ahead and throwing away data. I just keep putting it into a rolling hash. If you have 100 gigabytes of zeros and 128 bits of random numbers, general security theory says you got 128 bits of entropy. So my way of saying it is, I can assume everything else is crap as long as what is good is actually good. There's also the fact that I'm going ahead and using an encryption function instead of the raw output of my random generator. Well, when you actually look at lots of output from random generators, sometimes you see correlations. Sometimes you see things where you get an insight into the internal state of the system. You know what I'd rather do? I'd rather use a cryptographic function that is fundamentally designed not to leak internal state. The third thing that might be wrong is that I'm not using the algorithms that are normally used for random number generation. I'm using crypto. Usually we use things like the Mersenne twister. Well, do cryptographic functions pass random number tests? So thanks to my friend Jamie Schwetman, we actually went ahead and took about 16,000 CPU hours and we ran the die-harder entropy test across 21 ciphers with inputs of either 16 megs of zeros or 16 megs of dev random output. Why? Because I was curious. Also because it was looking like it was showing me awesome data. It wasn't. Data lies to you. There are no obvious statistical leanings to the data. I do have some machine learning people looking at it. Prior knowledge has been awesome. Alex Jokulin has been awesome. There are no conclusive findings yet. We are going to release this data. I do have kind of a fun little tool that I made. It's called C-SQL. You pipe a CSV in, you can run SQL on the output, like just as a stream. So it's kind of nice. Some recommendations if you're a kernel person. Dev random can't block. Crypt gen random on Windows doesn't block. If it returns, it's going to return. If you call it, it's going to give you something. When I go ahead and do my RDP sweep and I find all the keys for RDP, let me tell you, 1 out of 200 of those keys are not going to be bad. Don't be so shy about your interrupt sources. People are being ridiculous and overly paranoid. Care less about interrupt counts than interrupt timings. You're in the kernel. You have a nanosecond clock. Use that. The ftrace functionality that's in Linux right now is very nice, and I almost used it to seed entropy, but it's on a microsecond clock. I want nanoseconds. Even if you're trying to go ahead and be nanosecond accurate, you're probably not going to pull it off. And then maybe consider this modified von Neumann construct. There's going to be debates about it. So that being said, our biggest problems in security do not revolve around random number generation. They revolve around languages, and specifically, so I've been working on something called language theoretic security with was working with Len Sassman and with Meredith Patterson. Language theoretic security is the hypothesis that security vulnerabilities are the consequences of the language's code is written in. So if anyone's an academic and you've heard of Sapir-Whorf, it is basically the statement that Sapir-Whorf is true for code. Corollary, if language got us into this mess, language will get us out. One way of looking at language theoretic security is through the lens of computability theory, to say that different classes of code have different amounts of power, and attacks are about increasing the amount of power that you have. This is a useful lens. But there is another lens that I happen to prefer. Does anyone remember diagramming sentences? Who would have thought that billions of dollars ride on people not understanding that? All injection is when the tree that I just showed you has bugs. Injection attacks are when a sending language thinks it's sending one tree and a receiving language thinks it's receiving another. The extreme example of this is when bytes flow out into surrounding memory and you get memory corruption. But SQL injection, LDAP injection, cross-site scripting, it's just situations where the sender is sending users data and the receiver interprets it as a peer's code. Well, so what? We got a new academic model. Who cares? Why does this matter? Because we really have to stop making fun of these attacks because they're the majority of all vulnerabilities, both written, discovered, exploited, and used to steal stuff. They're killing us. They're not leet. They totally work. Sorry. We have not actually fixed these problems. If we did, they wouldn't be costing us so much. So yes, if you're, so we're going to talk about interpolate and where we're going to go with this, if you've ever heard of that. So the importance of this theoretical model is it declares the rules of the game. One, we need to start synchronizing parse trees across languages. Two, we want developers to actually use our method. See, we have a term in languages for languages that are not spoken. They're called dead languages. Who wants to work on something that's dead? This mechanism explains something that's surprisingly not understood. People don't seem to understand why XML got really popular really fast. It's because it allowed you to communicate with stuff written by someone else without spending like 4 months figuring out if the 8th bit of the 4th byte changed everything about the way something was parsed. It basically saved you from fiddly, detailed work just to exchange a silly parse tree. Why did JSON become popular? Well, because XML figured out its own ways of becoming fiddly. We got a hard truth here. The hard truth is that developers are in charge, not the architects. They love ASN1 and XML and WS, oh my god. It's not the academics that are in charge. They write Haskell. It's not management that's in charge. They love money. You don't get some money, performance, reliability, maintainability, features, rapid development, all things that developers are in charge of delivering. Money might be lost by security later. Who's not in charge? We are not in charge. Devs are in charge. We're going to start giving them useful stuff. You know what devs like? They like their code to work. So, biggest explanation out of language theoretic security is why is PHP so popular? First of all, if you don't think it's popular, I got a river. You can look up which one it is. PHP is incredibly good at copying and pasting code. We understand that CPAN makes Perl a thing, that you can just go ahead, get a library, and move on with your day. We don't understand that PHP sample code has the same effect. Java is hilarious. Java basically says, look how much code my IDE can write for me. Guys, this is copy and paste embroiled into your editor. Don't make fun of this stuff. This is actually how things work in the real world. So the language success metric, if we're going to actually succeed at fixing these bugs, what are the odds for a developer that if they try to do something, it's going to actually work? Note, I didn't say fail fast. Developers don't go to work saying, man, I hope this fails quickly. No, they say, I hope it works. I hope I don't have to debug this. I hope I can move on to the next 83 problems that are on my desk. Nobody tracks this metric, least of all us. We just say, hey, it's possible to write secure code. We're done here. Management will fire that dev if he doesn't do what we say. Bull. Management's not firing anyone but you. This is why all the successful languages tend to be the brainstorms of one guy. Because people can walk up to this one guy and be like, what the hell is that? Art is science before we know what we're doing. So PHP tends to be your favorite language. And if we're going to fix security, here's a good place to start. So what's wrong with object relational models? Object relational models say you don't even go ahead and you don't run SQL, you don't run any database language, you write everything in your normal language. It's just there. All the magic happens behind the scenes. Now this is wonderful until the moment you need to make a query. And let me show you something. Anyone know what this is? Brainfuck! I love this language. Brainfuck has a rejoinder. You know what that is? The rejoinder is there's more things in this world broken by punctuation than just brainfuck. Look, I got this thing here, result from name, in, names, where, name, sterling, name, lesson. There's 32 characters of punctuation in there. If I do SQL, I got 12. I got these huge gaps between it. Which would you rather write? It turns out, and this might surprise you, SQL is a language that is shockingly good for structured queries. It turns out that lack of punctuation. There's a reason we keep using it, guys. Turns out this matters. So our normal solutions for making SQL work, well, we have escaping. Look at this. We're not even trying MySQL real escape string. It's like 25 characters. What says you're not even trying like 25 characters? Bigger problem is it fails open. Code works if escapes are missing. And also it's a blacklist. When's the last time you saw a blacklist work? And so the solution is supposed to be parameterized queries. We'll go ahead and we'll declare a template, and then we'll individually poke our various variables into the template. How's that working out for us? We have to threaten developers with being fired. Okay? That's a data point. Look, when we actually go ahead and audit people's code, even like security developers, what do we see them doing? They go ahead and they say, these are the calls that might be unsafe. Okay, we'll parameterize those. But all of these other ones, no, we're just going to go straight forward. It's kind of interesting. I don't see any databases that offer the ability to require parameterized queries. It's like no one's demanding that. More interestingly, it is a crapshoot whether you get to parameterize. Go ahead and try to parameterize select. It won't work. That's because you actually have a fairly complicated parse tree, like I showed you a few slides ago. And sometimes you can go ahead and make it a parameter, and sometimes you can't. So in 2010, I released a package called Interpolate. It was a basic strategy for retaining developer-preferred style and still going ahead and stopping injection. And the idea is when you look at this string, select star from foo where x equals x and y equals y, humans can see the separation. Because look at that, there's that dollar sign. That says that's data and everything else is code. And that says that's data and everything else is code. And it's beautiful, except the language throws it out. What if it didn't? What if we actually had PHP say, wait, that was plain text, that came in from a variable, let's treat them differently. So the original approach for Interpolate went ahead and had this alternate, caret x and caret y. The call would be turned into our nice preferred parameterized query, and then you'd eval the blob, because that was the only way you could dereference x and dereference y and find out what your actual variables were. The problem with Interpolate, and there are a couple, but this is the biggest one, the problem is when the developer actually goes ahead and instead of having my little interpolation syntax, actually uses the dollar sign. So here you go ahead and you have x and y, they're attacker controlled, and they're one function away from being evaluated in the web front end. Like this B function can go ahead and look at the code and say, wait, this thing, if PHP gets its hands on it, is going to cause a bad time. It could do that, but good luck predicting what PHP is going to do with arbitrary bytes. So this is scary failure mode. You got to care about that. So how do we build a safe Interpolate? Well, eval only exists that the variables from the calling scope can be dereferenced. What if we can go ahead and write a function that goes ahead and is able to say, wait, you want x, you want y, and you want them from the parent? You want them from the thing that I'm called? Sure, I have access to that. It's heresy from academic circles, but they like Haskell. I'm not writing in that either. This would require a patch to PHP, and Daniel Zula is actually writing this code now. It's very nice. Now, some people have said, why don't we just patch the original code? Why don't we actually rewrite the code automatically? Has anyone here ever audited auto-generated code? It's not fun. I'm not a fan of doing it. There is an argument for tainting. So the idea here is that we take our variables that come in off the wire, they come in over HTTP, and we go ahead and we mark them and we say, these particular bytes are bad. They come from evil. Not this entire variable is bad, but these characters here, you better go ahead and treat them properly. And that's actually not the worst thing. Then you can have a function that goes ahead, it gets a string, it looks in the string and says, show me the string bytes that are safe. I'll go ahead and I'll send them raw. The ones that aren't, I'll go ahead and I'll specially treat or put them inside of a parameterization or whatnot. We're also writing that. Superencoding. This is actually really cool. This comes from some discussions with Zane Lackey and Nick Galbraith over at Etsy based on a thing they're already doing in production. What if all variables from the web didn't get this like weird modification to the underlying string API in PHP? What if we just go ahead and we hex encode them? So that when they fly through our application, they're always hex encoded, and when the function goes ahead to throw it into the SQL database, it says, things that are hex encoded I have to treat special and not go ahead and let them inject. This is not a bad approach. It does require accessor methods every time you go ahead and use these variables, but that might actually work. A last-minute alternative, and I mean figured out a day or two ago, we could go ahead and instead of marking the dangerous stuff, we could mark the safe stuff. We could go ahead and we can say, the actual SQL that you use, that needs to be hex encoded. And then that's picked up either in a front end to the MySQL call, or you actually modify MySQL. You tell the MySQL Lexer, hey, you don't accept code unless it's been specially marked. And the advantage of this approach is, guys, we're not throwing SQL around that much through all of these various depths and functions and whatnot. Usually you have your SQL and then you have your call, which is kind of nice. This is what langsec means. You actually start saying, what are people trying to say? How can we make it easier to say that? How hard is it going to be for people to migrate? Guys, if you don't care about developers, they're certainly not going to care about you. Two more things. It doesn't matter what code people are writing if there are parties in the middle that are planning on changing everything. And interestingly enough, Verizon is claiming a First Amendment right to edit your First Amendment rights. That's cute. Entire countries are blocking web pages. I think Indonesia announced that they're going to block 1 million porn sites in the run-up to Ramadan. Somehow I don't think those sites are going to get unblocked after. Last year I wrote some code called neuter. And neuter is beautiful, okay? Neuter is a really fun mechanism for detecting network manipulation. Basically, you have a client, you have a server, and they scheme to make it look like they're speaking speaking YouTube and speaking BitTorrent and speaking all of these various protocols and sites, and in an attempt to get the man in the middle to apply different policies to communication between the same parties. Unfortunately, neuter requires a whole bunch of really low-level packet tricks. Which means you basically have to deploy hardware. Has anyone here ever deployed hardware? It's not fun. It's not impossible, but it's definitely improbable. What can we do to do better? Well, we could use executable code on the client. That's what Uniprobe is about. We could use web pages with iframes. So when you go to Herdict, it pulls in, throws up a frame, and says, do you see a web page in here? You have to click yes or no. Maybe you have an extension that automates that a bit. Is it possible to determine whether content is up or not just from a web page? Basically, can we crowdsource data on censorship in the world? If you want the biggest crowds, the game is to maximize the amount of data you get per user and minimize the installation load per user. Can we do that? Well, browser same origin policy usually says no. Yahoo's not allowed to know anything about Google. Google's not allowed to know anything about Microsoft. But there is an exception. Everyone is allowed to load images from everyone else. And not just that. They're allowed to know if the load worked. And not even just if there was a file there, but if there was an actual image at that address and if it could render successfully, and even what the dimensions are. So this is kind of neat, because if a domain is being censored, the image is not going to load. What one image is on most domains in the world? It's called favicon.ico. You can see it. It's this little thing next to Google right there. So we wrote this thing for the Wall Street Journal Data Transparency Hackathon, me, Joseph Van Geffen, and Michael Tiffany, called Sensor Sweeper. What it does is it tries to load images from all of these domains on the internet. If they load, it drops it into this map. If it doesn't load, it drops a bomb. So that bomb is for this site doesn't exist.xyz. What's actually happening in JavaScript is we create an image object, we attach an onload and on-error handler, and then we go ahead and we tell the object, OK, here's a source for you to load for. The above is done in parallel, reading from a list of sites that we've confirmed have a favicon.ico. And if we get 6 failures, then we drop a bomb. Is that enough? No, actually it isn't. Web browsers provide surprisingly little feedback into whether a failure has happened and why it's happened if it has. Flow control really has not been implemented for the web. It's embarrassing. So for reliability's sake, we have to basically shut down all other lookups and then do 2 lookups. One to a domain we know is up, and then one to our test domain. We have to do it basically simultaneously. That said, Sensor Sweeper works pretty well. Can we do better? Well, once upon a time, 2007, you could actually treat browsers like VPN endpoints, like open proxies on the internet. If someone came to you, you could go ahead and use browser sockets and connect to anyone through some interesting tricks. We fixed those tricks. Now you can only create connections back to yourself. Except sometimes there's someone in the middle between the browser and your server, a web transparent proxy. There's more details on this from my paper, Staring into the Abyss, and from Bob Opger's paper, which is foreshadowing socket-capable browser plugins result in transparent proxy abuse. So we've known this, but we've never explored their use for detecting censorship, because often it turns out censoring devices are implemented via transparent proxies. So here's what we can do. You can go ahead and create a Flash object on some web page, have it connect back to your port 80. You send an HTTP request for Google, for Yahoo, for whoever. If there's no transparent proxy there, it's just going to come, the request is going to come to you, and sorry, it's one of the 80% of hosts that has no transparent proxy. But 20% of the time, if you ask yourself for Google, something in the middle is going to say, oh, you want Google. Here, let me give that for you. And sometimes that content is not going to actually be the actual Google. It's going to be the censored content or the censoring announce. So that's kind of neat. It turns out this extends to certificates, which was kind of cool. You can go ahead and you can run an SSL connection back to yourself. And you can say in the actual client, hello, me, I'm looking for Facebook certificate. Might you have a copy? And something in the middle might be like, oh, have I got a Facebook certificate for you? See, the thing in the middle doesn't realize that's not actually the browser, because the browser's not going to tell you what certificate it got. But my little Flash object, totally. That's kind of neat. There's no way of asking the browser DOM what certificate hosted content. But you can go ahead and use these Flash objects to do that. Now, there's some limitations. You can test any certificate as long as the man in the middle is not doing DNS hijacking. The Flash app is going to an IP address, not to a DNS name. So if you go ahead and Facebook is being moved by DNS, you won't go to the IP address that would have been provided for Facebook. But you can always test your own certificate at least. Full proxying, this is kind of neat. One of the difficult parts about writing all of these tests is you need to actually implement all of these protocols in Flash or in Haxi. Wouldn't it be nice if you could just go ahead and run normal code, and just proxy it through the browser? Now, this was written before, back in 2007 when we had full access. It turns out we can do it again. We can go ahead and we can take an entire web browser on the server, we can squeeze its traffic up back to some web browser out there. That web browser is going to go ahead and send all of that traffic back to the original server. And the original server can then go proxy it to the entire internet. Why would you do this? Because it very much looks like these hosts in the middle that are altering content are not IP sensitive. They don't care who you're talking to because the IP's changed too much. So if you can talk to anyone, you might as well talk to yourself. So 11 minutes left. Let's talk about the last but not least, how do we scan the internet really, really fast? Actionable intelligence, important thing. What can an attacker do today that he couldn't do yesterday for what class attacker to what class victim? Every time you see a security vulnerability, this is the question you have to ask yourself, and a lot of people don't. Related to this question is, well, how many victims are there? So I've run 2 major scans this year that I've talked about anyway. One is for Telnet, which was determining the presence of Telnet encryption because there was a really bad bug there. The answer was there's just not that many Telnet bugs. The other one is RDP. How many people are stupid enough to go ahead and put, remote desktop on the open internet? It turns out like 4.1 million people will do that. So that's really common. People have asked me, well, how are you actually running these scans? So once upon a time, I wrote a tool called ScanRand, and what it does, it just sends TCP connection requests called SYNs to tons and tons of servers, just spews them out on the internet. And then look at the responses that come back and go, aha, port 3389 is up, therefore there must be a RDP server here. Turns out you can't do that anymore. There's tons of IP addresses that will totally nod and say, yeah, there's something here, but when you actually try to talk to it, there's nothing there. So you got to actually talk to these endpoints or you'll just get the wrong answer. So the solution that I had originally was a split process. Identify the candidate IP addresses that are listing on a given port, and then given a candidate, actually connect to a particular IP address. Candidate collection, we go ahead and we spew the SYNs, we increment the first byte first. This means the larger a space you're scanning, the slower you're scanning each individual network, therefore the lower the chance that you're going to overload a particular net. It's a completely separate process with TCP dump. We go ahead and we capture all the syntax. These are the first pass messages that say, yes, there might be something here. Now, for the Telnet game, the Nmap team in like 24 hours actually wrote me a test. It was awesome. So I just fed my IP addresses from the syntax right into Nmap, and it gave me answers. For RDP, I ended up writing my own test, and I used an amazing framework called Black Mamba. It's probably the most pleasant environment for reasonable scale TCP probing ever devised. You just basically write normal socket code, and every time it might block, you put in a yield. So you're like, connect, and then yield. Come back when it's done. Write, and then yield. Come back when it's done. Really nice to play with. Sometimes you have to go ahead and increase your operating system limits, but you'll get about 3,000 IP addresses a second scanned this way. It works okay. What do you want more? I've always wanted to write a network stack. A little while ago, H.D. Moore actually kind of kicked me into doing it. He's got a super mysterious project called critical.io. And I am nothing but not willing to support mysterious projects from H.D. Moore. So I've been writing ScanRand 3. ScanRand 3 is a new scanner that doesn't just flood SYNs, but actually manages all the connections and extracts data. Now, originally, I was going to have like a full network stack with state and keep track of everything, and I was going to use SQLite to go ahead and be the state table. Why? Because I thought it'd be hilarious to manage retransmits with a SQL call. It's like star from sockets where data sent is not data acknowledged, and data sent time less than now is greater than 3 seconds. This was funny to me, okay? I entertained myself. SQLite in memory-only mode is totally fast enough to do this. You get like 160,000 inserts a second. The moment you try to add some indexes because you want to be able to query this data that you're throwing in, yeah, then performance falls into a bucket. You get down to like 20,000 inserts a second. It's a new plan. I don't want to keep state. Can't someone else do it? Let the servers keep track of all of these connections that I got. I was curious, was this actually going to be possible to do? So here's what it turns out actually totally works. You send your initial connection request. You send your SYN. And it says, hey, I want to talk to you, and I only want you to send me 1460 bytes at a time, a single packet. Whenever you happen to receive a SYNAC, an acknowledgement that someone wants to talk to you, you go ahead and you immediately send them a payload, get/HTTP 10. Yes, it turns out you can put a payload in the initial acknowledgement. Then, when you receive responses, when you actually receive payloads, you say, great, thank you for the data. I'm going to go ahead and save this, store it into a database, whatever. If there's a payload, you'll go ahead and say, thank you Sir, may I have another? When you get the final message, it'll be marked as it with a FINAC. Then you say, thank you for that data, reset, go away, I don't want to talk to you anymore. At no point am I storing any connection data. However, every single time a packet is dropped, except for my initial packet making connection, the other side says, hey, you didn't acknowledge my transmission. Let me send that to you again. So you end up with this situation where you are not storing any state, you don't have any lookups, the other guy is, and you end up scanning like 80,000 IP addresses a second. So you can go ahead and run this, and I don't have time to do the demo, but you can do 3.25 million IPs, takes 80 seconds, you get about 800 megs of content. You reassemble your data with a SQL call. It's very nice. The task is embarrassingly parallelizable. It can parallelize across IP addresses. The databases can be independent. This is a low-end number. I mean, it's 80K now. It'll be hundreds of K, if I ever care to. This is on a $200 Opteron box with 2 CPUs. Security. How do we actually make this safe? Right now, we don't. Anyone can just go ahead and lie and be like, oh yeah, this server totally has all this content. But ScanRand in its original form would put a cookie into the actual TCP header, a secret value that someone would have to reflect back to you. They would have to have seen your request in order to put it into a response. And it turns out you have about 48 bits that you can put secret values into. You can put them into the sequence number. You can put them into the source port. There's another 32 that's possible by putting them into the timestamp, but that gets a little wonky because things keep track of timestamp orders. It is a bit of an issue that the more data you send, well, you're sending data, which means you're advancing the sequence. This thing that used to be not changing is now actually changing. But it changes at fairly predictable points. Some notes, kernels have gotten faster. Somebody's going to go ahead and say, wait, my awesome socket code through my crazy incantations is better than your user space code. And that might happen. I tried some stuff with non-blocking connects and ePOL, and it looked like it could have been fast, but I couldn't get it to work right. Wrong incantations. But my approach eventually becomes the fastest. It has to, because I'm not actually doing any work. This is success through laziness. I do need a way of telling the kernel, hey, I have like 1,000 packets for you. Don't make me keep calling you. Here, send all of these. Or even better, here, send this list of IP addresses. Couple more notes. There are faster databases than SQLite. If nothing else, I can just have a giant allocation of memory and then go ahead and for every IP address I get back, I jump to that particular address in the allocation. There's also a project called MemSQL that I plan to play with. MemSQL is a fork of MySQL that's entirely focused on memory-only operation. Every SQL call is then compiled down to C++. So maybe I'll get to do my query across my quote-unquote sockets with SQL after all. There are also merged approaches where I go ahead and I don't start tracking state until someone shows that they're actually there. We'll tell you this, though. There are a few servers out there that had the same idea. They're like, we'll be stateless servers. The client will track everything. So the client thinks the server's tracking everything, and the server thinks the client is tracking everything. Yeah, well, those machines I have a pretty high error rate for. But you know what? Whatever. I'll go ahead and I don't have many of those. I'll slowly connect to them, or I'll retransmit, or whatnot. Final question is, what should the coding model be? How do I actually, right now I just have a single call. Get slash from HTTP 1.0. What if I want to go ahead and interrogate the data if my second packet depends on the first? Maybe I call out to JavaScript or Lua. Maybe I go ahead and support. Nmap has a great support for being able to actually communicate with a peer host and query it for stuff. So maybe I'll implement support for that. Most important feature is a blacklist. I don't have that yet, which means I'm not going to scan the entire internet with it. Most networks don't mind getting swept, but some do. You got to actually respect that. And it turns out figuring out which IP addresses you don't want to talk to is a CPU-intensive thing. You have to match against the pattern. And you can't just use the operating system because, remember, we're bypassing the operating system. In fact, we're bypassing the operating system. Some people have said, well, let's go ahead and for every packet, we'll tell the firewall, no, 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 you don't respond to a kernel. I will handle it as a program. Don't play that game. Guys, just use another IP address. That's what I do. I just go ahead and I go on my LAN. I'm like, hey, I'm going to ARP for this new IP. It comes to my program. It's great. So that's a lot of stuff. Somehow I managed to stop on time. 34 seconds remaining. I hope you enjoyed. This may not be how you try to fix things, but it is how I do. Thanks to everyone at the sub who none of you have met for supporting me, and thank you for coming.